Hi, my name is Madi Gaines, and this is Lab 3, Black Hole for Physics 2211 at Georgia Tech. The goal of Part 1 is to find the mass of a black hole using a computational model. The goal of Part 2 is to also use a computational model that will help us find the initial velocity, which allows the spaceship to fly close to the black hole before leaving the black hole system. These are my findings from both parts of the lab at the bottom of the slide. The first key concept of this lab is Newton's second law, which says the net force acting on an object is the change in momentum divided by the change in time. This is also related to the velocity update formula and the position update formula displayed on the slide. The second key concept of this lab is the parallel and perpendicular components of the net force. They are equivalent to the components of change in momentum to change in time. The parallel component is parallel to the direction of motion and affects the speed of an object. The perpendicular component is perpendicular to the direction of motion and affects the change in direction of an object. These are shown in the equation form below. The third key concept is the universal law of gravitation, which states that the gravitational force on an object due to another object is an attractive force that is proportional to the masses of the object divided by the square of magnitude of the distance. The gravitational force follows Newton's third law, so the force on one mass is equal to the force on the second mass in the opposite direction. The free body diagrams for Part 1 and Part 2 are shown on this slide. For Part 1, the gravitational force on the star is used to find the mass of the black hole in Part 2. Multiple gravitational forces are used to find the initial velocity. The system in Part 1 is the star and the surroundings is the black hole. In Part 2, the system is the spaceship and the planet, and the surroundings is the black hole. For Part 1, the initial conditions are displayed on this slide. We can see the gravitational constant, the mass of the star, and the change in time. On this slide, we can see the important equations used in Part 1. These calculations include the net force, parallel and perpendicular components of force, and the equation to find the mass of the black hole. On this slide, we can see the iteration loop for Part 1 of the lab used to update the net force and position of the star. The mass of the black hole is remeasured after each iteration. The results of Part 1 of the lab are displayed here. The mass of the black hole is 2.44 times 10 to the 34th kilograms, which was calculated by finding the average of the black hole mass values from the iteration step. The star follows an elliptical orbit where the magnitude of the gravitational forces on the star is left at the farthest point from the black hole than near the closest point. A possible source of error is rounding values made during each iteration and for the constants. This explains the different mass values at each iteration. For Part 2 of the lab, the initial conditions are shown here. There is the mass value found in Part 1 of the black hole, and the initial velocity of the spaceship is the unknown. We found the initial velocity using the trial and error method. This slide shows the important equations for Part 2, the distances between the masses, r-hat values, gravitational forces, and net forces. These equations I then converted to Python code, as we can see on my slide. This is the iteration step for Part 2 of the lab. The results in Part 2 show the initial velocity is negative 4.8 times 10 to the 7th, 2.5 times 10 to the 6th, 0 meters per second. The shortest distance between the spaceship and the black hole is 2.4 times 10 to the 8th meters. The initial velocity shows the spaceship moves to the left and up. Surprisingly, the spaceship is shot away from the black hole by the gravitational force of the black hole, which increases the spaceship speed until the speed exceeds the escape speed. A possible source of error is the rounded values for constants during the iteration step. This would underestimate or overestimate velocity values. The parallel and perpendicular components of the net force are equivalent to the parallel and perpendicular rates of change in the momentum by the definition of the net force, which is equivalent to the rate and change of momentum. However, the net force in Part 1 cannot be calculated without knowing the masses of the black hole and star, while the rate of change in the momentum of the star can be used to find the net force and its components. To test the weather question, the initial velocity of the spaceship should be less in magnitude in the x direction and greater in magnitude in the y direction. The new initial velocity would allow the spaceship to orbit around the black hole. The new velocity is negative 1.6 times 10 to the 6th in the x direction, 1.3 times 10 to the 7th in the y direction, and 0 meters per second in the z direction. It would orbit around the black hole after 90 minutes.